This video explains the first two cases of parallel operation of pumps discussed in details in another podcast, namely two same or different type parallel connected turbo pumps installed in a common pump station and located close to each other. You can find the link in the video content. The installation diagram is also shown in this Excel workspace. You can see it here. The main purpose is to demonstrate in practice the graph-analytical determination of the operating parameters of the pump system as well as the individual pumps. However, preliminary preparation is needed to facilitate and better illustrate the proposed methodology. This includes the downloading of the pump operating curves catalog data, which in this case are Bulgarian pumps of the type 6E12 and 12E12 produced by V-Pump company. Then, the pump operating curves should be scanned as described in another podcast. The link is also given in this video content, which enables the values of the coordinates of a certain number of points of the two pumps curves to be transferred into Excel. So that's how we got these values. Now, let's focus on the graphical part of the solution. To determine the operating mode of the pump system, it is also necessary to plot the pipe system resistance curve. First, indicate whether or not the pump system has static head. Let's say that the static head in this case is set to be 10 meters. The value is given here. Then, estimate the relevant pipe system coefficient K of resistance. Depending on the specific features of the system, an appropriate equation for calculating K should be selected. Whether or not to modify the general form of this equation is described in details in another podcast. Of course, the link is also given in this video content. It is found that in this certain case, the value of this coefficient is 24,500, where the dimension is second at second degree per meters at fifth degree. When identical pumps operate together, for each head value, the corresponding flow rate is multiplied by the number of pumps, which means that in our case of having two identical pumps, we have to multiply the flow rate twice. Now it's time to do these simple calculations concerning the flow rate. So let's multiply each individual pump flow rate with 2. And here is it. Next step is to estimate the head energy loss in the pipe system. For this aim, a certain number of flow rates in the range from 0 up to a given maximum flow rate should be selected in a certain step. Let's show it. So we start from 0 and let's say that the step is 2. So it will be 2, 4, 6, 8, 10, 12, 14. Let's say that 14 is the maximum flow rate that we are interested to analyze. So, for each of the set flow rates, the total head energy loss in the pipe system should be calculated. For this aim, we have to take into account that there is a static head in the system which remains constant. And we have to sum it with the multiplication of the summary pipe system coefficient of resistance, which is another constant, That is multiplied, with the relevant flow rate put at second degree. However, you have to take into account that the flow rate is given in liters per second, and the equation that we are using right now requires for the flow rate to be presented in its basic measuring unit, which is cubic meters per second. That's why you have to divide it with 1000. So here is it. Now we are ready to estimate the energy loss. Of course, when the flow rate is 0, the energy loss in the pipe system will be equal to the static head. And now let's see what will be the rest values. Okay, here is it. So now we have to plot the three curves in a common coordinate system and get ready to specify the intersect point. Let's start with the pump individual head curve. As for this aim, we need to take these values, these concerning the flow rate and these concerning the head. So here is it, the pump individual head curve. Okay, now let's plot the summary head curve of the two pumps. So this is the summarized flow rate, and we have to use the same values for the head. So now we have both these two curves, the blue line, which is related to the individual operation of the pump 6E12, and the orange one concerning the parallel operation of the two identical pumps. So now let's plot and the pipe system resistance curve. For this aim, we have to select these values concerning the flow rate and these values concerning the head energy loss in the pipe system. So finally, we have plotted the three curves in a common coordinate system. So here are the two intersect points. This one concerning the parallel operation of the two pumps, and this one concerning the individual operation of one pump. After the completion of the graphic part, it comes the turn for analytical determination of the operating parameters. For this aim, it is necessary to copy the pump curves diagram and transfer it into another Excel workspace. So let's paste it here. We have to do this because now it is easier to obtain the equations describing these two curves. It is well known that with sufficient accuracy, these two curves could be described with full second degree polynomials. So let's do it now for the first one. Oh, sorry. Okay, so to make it clear that this is the equation concerning the summarized head curve, I will highlight it with the same color. So let's do it orange. Okay, so now let's repeat the same action, and for the second curve, the individual head curve of the pump. So at thread line, select second degree polynomial and display the equation on chart. Okay, so let's color it in blue and highlight it, so to know that this is the equation concerning the individual head curve. Okay, almost finished. So now we have the two equations that I'm gonna use for the analytical part of the solution of this problem. About the pipe head curve, it's not necessary to do it because we already know the values of the static head, which is 10 meters in this case, and the coefficient K of resistance, which represents the coefficient of parabola describing the curve. It was 24,500. This is something that we already. Now let's do the calculation. For this aim, we have to fill the gaps in the table, and A will be A minus K, where A comes from the equation of the summary head curve of the pump system. So it will be minus 0.039 minus the value of the coefficient K, but it's very important to remember that you have to divide this value with 1 million because initially it is used for the flow rate replaced in cubic meters per second, and now we use liter per second, and the flow rate is at second degree in the equation. So it's very specific moment that has to be taken into account. Okay, so we already have the value for A. B will be 0.2625. I'll take it from here. Okay, and the next coefficient will be C, which is 14.374 minus the static head, which we know is 10 meters. Okay, and the last one is the highest value of A. So we just have to multiply this with 2. Okay, now the gaps in the table are filled and we can move forward to the final estimation of the system summary flow rate. Okay, so just follow the above equation. Okay. Minus B minus, we have to open brackets, B put at second degree, minus 4 times A and C. I have to close the brackets and put this at the relevant rate. Okay, so one again, we have to close the brackets, and at the end, it has to be divided with 2 times A. So you see that the final answer for the summary flow rate is 10.62 liters per second, where a simple check on the graph is enough to validate the result. Here is the intersect point, so it can be seen by eye that the approximate flow rate is between 10-11 liters per second, so 10.62 could be accepted as the correct value. So once we know the flow rate, there is absolutely no problems to find the system head. So for this aim, just use the first equation, where the head will be equal to minus 0.039 multiplied with the flow rate put at second degree, then plus 0.2625 multiplied with the same flow rate, and then plus 14.374. So here is it, the value of the head. We can make a simple check by using the graph, and you can see that once again it can be used as validation of the result obtained. In case of identical pumps operating together, The flow rate of each one is determined by dividing the total system flow rate by the number of pumps. In this case, we have two pumps operating together, so I need to divide this value with 2. The head of each pump will be equal to the pre-calculated pump system head, so we already know its value. Determine the operating parameters of one of the pumps operating individually. It is necessary to use the equation of its head and pipe system curves. For this purpose, we are going to use the same type two-row table like the one above, but the determination of the coefficients will be done with the equation highlighted in blue. Just remember, this equation describes the pump individual head curve. So let's now copy and paste this table. Then we have to clear the old data and fill it with the new one. So for A, we're gonna have minus, I'll take it from here, 0.156 minus the value of the coefficient K. Don't forget to divide with 1 million. Okay, now for B, I have 0.5251. Okay, the next coefficient value will be 14374 minus the static head, which we know is 10 meters. And the last one, you have to multiply twice the coefficient for A. So the gaps are filled, and now we have all the data that we need, so to use once again this equation and estimate the individual flow rate of a single operating pump. So we have to put minus B squared minus 4 times the multiplication of A and what we call C. We have to put it at the relevant rate, close the brackets, and finally divide with 2 times A. So here is it. This is the flow rate in case a pump operates individually in the pipe system. For the head, we just have to use the equation describing the head curve. So once we know the flow rate, the head will be minus 0.156 multiplied with the flow rate squared plus 0.5251 multiplied once again with the flow rate and plus 14.7374. So here is it. We have finally the values of the operating parameters in case only one pump operates in the system. An interesting fact to be indicated is that if you compare the values of these flow rates, it seems that when a pump operates individually, the flow rate will be higher than if the same pump operates at same conditions but connected in parallel. For the case of parallel operation of two different pumps, it is necessary to take into account that each of them will have a separate individual head curve. So let's use the relevant data. We have this in advance. So to plot the two curves, let's start with the head curve of the first pump, which is the pump 6E12. So we can insert the Q data and the relevant H data. And here is it. Now let's move forward to the next one. This is the head curve of a pump 12E12. So the Q data and the H data. And here is it. Now it's necessary to display the equations describing these two curves. You already know that we use second degree polynomial. So let's highlight the equations with the relevant colors. This concerns the second pump. So let's put it in orange, and now let's display and the second equation, which we're gonna color with blue. In this case, the determination of the total system flow rate is accomplished by summing the individual flow rates at certain value of head, realized by each of the pumps at these heads. But you see that the initial data that we have is obtained at different head values, which requires now to recalculate the flow rate of one of the two pumps in terms of the head values of the second one. So let's put here Q recalculated. And how can we do this? It's simple. We're gonna use the equation concerning the relevant pump. So I will recalculate the values of Q for the second pump 12E12, which means that I'm going to use the equation highlighted in orange color. So for this value of the head, like any other values of the head, is related to the relevant values of the flow rate. But now we need to recalculate all these values in respect to the head values concerning pump 1. For this aim, we have to solve the quadratic equation describing the relevant pump head curve, the equation highlighted in orange color. So let's prepare a table, two-row table, similar like in the previously discussed cases, but you have to take into account that now we are not going to use the pipe system resistance curve equation, and we are only going to apply the equation describing the pump head curve. And because there will be 9 different values of the head that we want to use in the recalculation of the flow rate, we will have 9 different values of the coefficient C. So let's demonstrate now how to fill this table. For A, it will be the same like the coefficients in this equation. So it is minus 0.0412. Then we move forward to B. It is 0.1249. Okay, now about C, it will be 16.49, which comes from the equation, and minus the relevant value of the head. In the first case, it will be 14.5. So let's see what will be the coefficient C, and for the other values of the head. Now we've got it. And finally, we have to multiply twice the coefficient A. So now we have prepared all the data that we need so to recalculate the flow rate. Now let's use these coefficients so to recalculate the flow rate. For this aim, we have to take minus b minus b squared minus 4 times a multiplied with c. We have to close the brackets. Don't forget to put this at the relevant grade. And finally divided with 2 times a. So this will be the flow rate. This will be the flow rate, the recalculated value of the flow rate in respect to this value of the head. So now let's indicate which are the parameters that remains constant. So to simplify the calculations, the only changing parameter will be the coefficient c. So I will not insert this symbol here. Okay, and now let's obtain and the rest of the values. So now we have the recalculated flow rates in respect to these values of the head. So let's find the summary system flow rate. As for this aim, we have to sum the flow rate of pump 1 with the recalculated flow rate of pump 2. And now we are almost finished with the calculations. So now we are absolutely ready to plot and the summarized head curve for the whole system. As for this aim, we need to use these values for the head and these values for the system flow rate. Okay, let's plot this curve in the same coordinate system. So we need to insert the Q data, then the H data, and here is it. We finally are able to demonstrate the obtaining the plotting of the system summary head curve. So we can also plot and the pipe system resistance curve to demonstrate the specifying of the operating points. As for this aim, we're gonna use this Q data and this HV data concerning the head energy loss in the system. So now we don't need the equations of these curves anymore. Okay, so I can hide them. We can also change the starting value of the axis. Let's put 6. And now there is a better view of the final diagram of what we are looking at. As can be seen, the determination of the pump system operating parameters may be performed in a similar way as the previous case discussed in this video. However, determining the operating parameters of each pump requires to indicate the specific features of the system, as well as to take into account the equations describing their head curves.